the top title of my presentation in this problem for the abstract diffusion wave equation with Caputo fractional derivative. First, the formulation problem in the domain Hilbert space. We consider abstract diffusion equation 1, condition 2, where partial T alpha is the Caputo fractional derivative of order alpha in interval 1 to 2. Beta is interval 0 to 1. Where f of t given function belong to class and function q and c now elements of H Hilbert space, where H separable Hilbert space with inner product this form and norm operator A mapping H to H and arbitrary self-enjoyed densely defined positive unbounded operator in H. The domain of definition subset H. Assuming that operator A has a set positive eigenvalue lambda k and complete set of orthonormal eigenvalue functions EK. Let's say sequence of the eigenvalues of operator A have not finite limit point. Using renumbering of eigenvalues, we can number them in non-decreasing manner, that is following relations. Definition 1, a function u of t belong to class with the properties and satisfied condition 1, 2 is called as the solution of the direct problem 1, 2. Next formulation in this problem, given alpha beta number and given function f of t and p c, we find a function q of t in equation 1 satisfying the problem 1, 2 and initial condition 3, where mu is given function mapping segment 0 to capital T to R. Partial T is a noun linear bounded functional. The domain definition subset H mapping to R. Degree of study of problem in equation 1 when beta equal to 1 and q of t equal to 0 in the paper 1 after Laret and Sforza study a class of fractional diffusion equation in Hilbert space following type equation where alpha is interval 1 to 2 operator A is a linear set enjoyed positive operator. Thereafter introduce the notation of with strong solution for this equation and present condition under which there exists solution. Next paper after Hendricks, Mesquita and further studied a culture problem for fractional evolution equation following type equation where R greater to than 0 and alpha positive operator A is closed linear operator defined in the Banach space. The function f belongs to an approach space of x solid function. Next after paper after Rachmaninoff addresses finding unknown parameters in fractional diffusion models, proving the exists a unique solution. Main result, we investigate this problem for given function in the paper.
How are you? I'm good.
Following assumptions are made for given function. Condition E1 and N4, A4. These conditions, preliminaries let sigma be an arbitrary real number. We introduce the power of operator A action in Hilbert space according to rule A. The given sigma is power of operator A following form where hk Fourier coefficient of function A h, the domain operator A has the form. The information given to books. This book. Immediately follows from this definition that relation for n is sigma 1 greater than 0 and equal to sigma 2 on the set D of A sigma. We define in the product following form. For elements of set, we introduce norm. Solvability of direct problem. Theorem 1. For any C and C in H Hilbert space and F of T belong to class, direct problem 1, 2 has unique solution, and this solution has the form where T yacht of T, T yacht and T yacht corresponding Fourier coefficient of function f of t, t, c, and E alpha alpha and E alpha alpha minus 1 are two parameters meta-Leffler function. Prove this theorem. To solve a direct problem 1, 2 with that into problems. Problem 4, problem 5, where problem 4 equation no homogeneous, homogeneous condition. Problem 5 where equation homogeneous, condition no homogeneous. We first studied problem 4. So we defined operator. This takes form y of t h. This form. And operator a beta y following form. From the estimate of meta-Leffler function, and this is form, we have inequalities. This is inequalities. We have estimate A, where H in H Hilbert space. Let's consider explore abstract problem. Let's consider the following culture problem 9, where equation homogeneous condition is homogeneous condition. For this solution, equation 9, problem 9, following lemma holds. Let f belong to class beta in interval, then abstract culture problem 9 has a unique solution, and this solution has representation 10. The solution of abstract culture problem 9 satisfies following inequalities. 11, where S positive constant depending alpha and T, capital T. Problem this lemma. Let us that the solution to problem 9 exists. Then to complete the system of eigenfunction AK of the operator A, the solution will have the form 11, 12, where Tk of T now coefficient. According to 12 and 9, we have following problem. Where equation fractional ordinary diffusion equation where fk of t after a coefficient of function f of t. The solution certain problem has following the solution of problem can be expressed as 14. Then it's following that for T belong to class. We have this is operator A beta applied omega. For beta in interval and estimate metagrapher functions of metagrapher functions, we have following inequalities. We have following estimates, and in particular omega of t in class S of segment 0 to capital T comma D. By the original equation, we find partial T of omega, and where result we have partial T alpha omega belong to class and satisfies following estimate. This we have complex the relationality that 10 is a solution to problem 9. Let's move on to proof of the inequalities of the solution to problem 9. Suppose the problem 9 has two solutions, omega 1 and omega 2. Our goal is to prove that difference equals to 0. And hence the problem is linear for omega of t, where problem equation and condition no homogeneous conditions. Let coefficient omega k of t theorem from 15 is following that for any k, this is relations. Partial t alpha omega k t equal to minus lambda k beta omega k of t. Thus, we have obtained the following such problem for omega k of t. This problem has a unique solution. The given therefore we have omega k of t equal to 0 for t and for all k. By partial equivalence, we obtain omega of t equal to 0 for all t. Where result the lemma 1 is proved. Here we define the maps G operator mapping from class to class by following form 16, where f of t belong to class. Therefore, according to lemma 1, we have following estimate. And for problem 4, we have following estimate statement. Theorem 2. Let Q of t in class and f of t belong to class for some vector, then problem 4 has a unique solution and it satisfies following integral equation. There is constant S equal to constant such that following characteristic type inequalities. In 18. Let us write the couch problem for as following type. 19 problem. If we take F, then according to solution 10 of problem 9, we obtain an integral equation equivalent to problem 19 with respect V1 of t. Integral equation 20. For integral equation 20, we apply the theorem of about general Fox point theorem. Fox point. So we look for fixed point of operator O defined by this form. For V1 belong to class, we apply to operator O to V1 with in a row. We have following. By inductions, we apply operator O to 1 and time. We have following operator O and V1 of t. Here we don't zero time applied is identity operator. By Q of t in class and V of belong to class, we know that Q multiplying V1 V belong to class, and where following includes false 21. By estimate 8 for V1 for all t, we have following inequalities. Then for every V1, we have G operator applied to V1, which belong to class, and the estimate false. Thus we can see that G maps this class into itself. Combining GF belong to class, we get that operator G also maps class into itself. Repeating the sum conclusion for V1, V option, this is estimate. By induction for V1, we have estimate 22. Therefore, we have G of Q over N of V1 belongs to class with S of segment 0 to capital T gamma D of A beta. Therefore, for V1 V1 2 belong to class, we have difference inequalities. It adds to every tends to 0 as and tends to infinity. Times this relation. Therefore, we have inequalities for essentially large n, that the operator O n is contraction mapping from this class to itself. Hence, the mapping Gn admits unique fixed solution V1. That is Gn V1 equal to V1. Here, since following relations. The point GV1 is also a focus point of the mapping G1, Gn. By the units of the fixed point of Gn, we get GV1, GQV1 minus G of F equal to OV1, then equal to V1. That is the equation 20 has a unique solution V1 in class. For n, we have this is relations as GF belongs to class, and by 20 and 22 we have following estimate, and by taking scientifically large k we get following this estimate, where S depending on alpha and capital T. By 23 for all T we have V1 belong to this D of alpha A beta. This form, and by estimate 8 we have this estimate for this. The mapping T belongs to class that for this estimate false. Therefore, we have following estimate 25. By the original equation, we find partial T alpha V1 after the V1 21, 23, and 25. We have this partial T alpha V1 belongs to this class with the estimate false. Their result, the theorem 2 is proved. Now, similar to problem 4, we will investigate problem 5. Theorem 3. Let T say this is class for some beta and Q of T belongs to class. Then the problem 5 is a unique solution V2 this class and satisfy following, and where we have this integral equation where Z1 of T and Z2 of T following form in class, and the operator G defined in 16. There exists a constant, positive constant S depending on alpha, beta, capital T, and norm Q, such that estimate 27 false. From this theorem, with the solution V2 of 5 into V2 equal to capital omega pi less nu, where capital omega satisfies problem 28 with F0 of T. This is form where nu equal to 5 kilo 6 pi T T. By the condition of theorem 3, we have this F0 of T belong to class, and the estimate 29 false, where nu satisfies this inequality. By theorem 2, and then the problem 28 is a unique solution W satisfies satisfies the properties and the estimate. Therefore, the problem 5 admits a unique solution V to this class. It satisfies the properties. And the estimate 27 false. Therefore, we have established the existence a unique and regular of solution direct problem. Theorem 4. Let function Q, P, and C and F following belong to class for some beta and Q of in class, then there exists a unique solution U belong to class to direct problem 1, 2, such that partial T alpha U in class. Moreover, there exists a constant, positive constant S, such that following estimate holds. And we get 31 integral equations for function U of T, where Z is defined by 16. Theorem 5. Under the same condition as theorem 4, the solution of the direct problem 1, 2 depends continuously on the given data, that is, satisfies conditions, where S positive constant depending on alpha T and normal Q. For theorem 5, let function U and head U be the solution to direct problem 1, 2 representativity to the function, this function using function U of T equal to V of T minus double V of T. We have following inequalities where V double V and V head and double V head corresponding to the data function respectively. Using 17 V option following inequalities. This is equals integral inequalities for this difference. Then, according to Romanovskiy inequalities, the option, this is estimate 23, where S positive constant depending on alpha, capital T, and normal function Q head. There is some arguments as applied to 31 before led to this difference 34, where S depending on alpha T and function Q head. Finally, from 33, 34, we get the great estimate 32. The theorem 5 is proved. Next, we investigate inverse problem. Inverse problem 1, 3. The following make the result hold. The inverse problem, theorem 6, let condition A1, A4 be held. Then the problem of finding solution of inverse problem 1 and 3 is equal to problem of determining of the function Q of T. Satisfies integral equation 35, where A beta U of T is form 36. Proof this split the proof into two steps. two steps. Supported inverse problem 1, 3 has a solution Q of t, taking into account conditions A2 and Apple partial t to equation of 1. We have this is equation 7, taking into account condition 2, 3, and obsession condition A2, A4, we have following. From this is relation, we have following equation for Q of t. From this, we have a relation 5 of equation theorem 6. Next step 2. Support now that Q of belong to class satisfies 5, or to prove that Q is the solution to the inverse problem 1, 3. It is to show that 3. By the equation 1, we have 37 together with 35 and condition I3. We option that Y, where Y satisfies following problem 8. Therefore, we have integral equation for Y of t. Homogeneous integral equation. Then for Q of t in class, we have inequalities. Inequalities that homogeneous integral inequalities. Hence, according to Granoll inequality, this equality, we have norm y equal to 0 for all t, which implies partial t of u equal to mu of t on the segment. The theorem 6 is proven. The next theorem has exists solution in this problem. Theorem 7. And the openness I1, A2 be satisfied. There exists means small t such that the inverse problem 1, 3 has a unique solution, and this solution in class. Prove theorem 7. Let us define the following operator. Operator Q 39 to prove that the operator Q means a fixed point, start by showing that maps a version closed convex set into itself and the space. First, we will show that there exists a positive constant T1 such that for any T, there is a rather positive I such that closed convex ball BF is separated by the operator Q that this ball itself BR. That is Q of BR subset BR. According to the definition of operator AB and linearity and two conditions I4, we have following. And by the folder inequalities, we option 40. Then for any Q in ball, and from the linearity of partial P and to condition A4, we have following. Partial P of T. And therefore satisfies T tends to minus 0 limits equal to P0. Now we take R such that R equal to P0. Then we can choose sufficiently small T1 such that satisfies uniqueness. For all T, we have uniqueness 41. And next, now there is the second condition of the fixed point theorem. Let Q of T and Q hat of T in BR given. Then for the difference of the operators, we have following difference by the linearity of partial P and condition I4, we have the following estimate, where S positive constant, the sum at 32. Therefore, we can choose potentially small T2 such that condition false for all T. The option following estimate 42. Estimate 41 and 42 so that Q is construction map on R for all T in interval 0 to capital T 0. If choose the capital T 0, this is false. Where we prove theorem 7. Thank you.